What Voyager 1 really heard in deep space beyond 3I/Atlas. There is a machine drifting through interstellar space right now. Not fictional, not theoretical. A real machine built by human hands in a California laboratory in the 1970s, powered by the radioactive decay of plutonium, transmitting signals back to Earth at the speed of light, signals that still take more than 22 hours to reach us. It is the farthest object ever made by our species. And in the weeks following the detection of 3I/Atlas, something strange happened. Voyager 1 began recording anomalies in the plasma density of interstellar space that nobody expected. Frequencies that didn't match any known background model. Oscillations in the electromagnetic environment surrounding the spacecraft that scientists are still, to this day, struggling to fully explain. This is not a story about alien signals. Let me be precise about that right from the start, because precision is the only currency that matters in science. This is a story about something potentially stranger than that. A story about how the arrival of an interstellar object of unknown origin appears to have coincided with measurable, documented changes in the physical environment of the space between the stars. Changes that Voyager 1, our only probe operating deep within the interstellar medium, detected with instruments that were never designed to last this long. And this is a story about what those changes might mean for our understanding of the galaxy. Not as a collection of isolated stars, each one a lonely lamp in an otherwise empty room, but as an interconnected system, threaded by fields and plasma and the passage of ancient matter from one stellar neighborhood to another. To understand what happened, you have to understand the place where Voyager 1 lives. Not lives in the casual sense, but exists in a region of space so remote, so physically different from anything within our solar system, that the rules change. The interstellar medium is not empty. It has never been empty. Between the stars, there is gas and dust, and magnetic fields and plasma, and cosmic rays streaming in from every direction. The shrapnel of ancient supernovae, the energetic exhaust of stellar death. For most of human history, we had absolutely no direct measurement of this environment. We had theories. We had radio observations from Earth. We had models built on inference and clever mathematics applied to observations made from inside the very bubble of solar influence that we were trying to see through. We had no probe out there, physically moving through that medium, tasting it, touching it, sending back data from the inside. Then Voyager 1 crossed the heliopause, the boundary where the sun's influence ends and the true interstellar medium begins, in August 2012. And everything changed. Not dramatically in the news cycle. The news cycle moves too fast for the pace of science. But scientifically, profoundly, permanently, we had a sensor in the void. The heliopause is worth dwelling on for a moment, because it is one of the most significant boundaries in our solar neighborhood and most people have never heard of it. The sun doesn't just emit light. It emits a constant stream of charged particles, protons, electrons, helium nuclei, traveling outward at hundreds of kilometers per second. This is the solar wind, and it has been blowing for the entire 4.6 billion year lifetime of our star. It fills an enormous bubble of space around our star, a bubble we call the Heliosphere. Inside the Heliosphere, the sun's particles dominate. Cosmic rays from the galaxy are partially deflected. Our planet is shielded from a portion of galactic radiation by this invisible magnetic fortress. The magnetic field throughout the interior of the Heliosphere is the sun's magnetic field, dragged outward and wound into a great spiral by the combination of solar wind expansion and the sun's rotation. The pressure balance at any given distance from the sun is maintained by the outward push of the solar wind against the inward pressure of the interstellar medium. But at the heliopause, everything the sun throws outward finally meets the pressure of the interstellar medium pushing back, and they reach an equilibrium. A wall, a membrane, a boundary layer where the physics transitions from solar to galactic. This boundary is not sharp in the way a physical wall is sharp. It has some thickness, measured in tens of millions of kilometers, which sounds enormous until you realize it is vanishingly thin compared to the distance from the sun to the heliopause itself, which is roughly 120 astronomical units, or about 18 billion kilometers. And on the other side of that membrane, true galactic space. The interstellar medium, the stuff between the stars. Voyager 1 punched through that membrane traveling at roughly 17 kilometers per second. On the day it crossed, Scientists watching from the Jet Propulsion Laboratory in Pasadena noticed something subtle and extraordinary on their instruments. The density of the plasma surrounding the spacecraft changed. Abruptly, the low-energy particles characteristic of the solar wind vanished. Cosmic ray intensity jumped. The magnetic field shifted orientation. The character of the electromagnetic environment around the spacecraft was fundamentally different from anything inside the Heliosphere. Voyager 1 was in interstellar space, and for the first time in the 4.5 billion-year history of our solar system, we were reading that space from the inside. What the spacecraft has been detecting ever since is called the local interstellar medium, the particular patch of galactic space through which our solar system happens to be moving at this moment in its long orbit around the Galactic Center. And here is something that most popular science coverage omits. The interstellar medium is not uniform. It is not a featureless expanse of homogeneously distributed gas. It is structured. It has regions of higher and lower density. It has waves. It has pressure fluctuations caused by distant stellar events that ripple outward through space like sound waves through ocean water. It has magnetic field lines that thread through it for hundreds and thousands of light years, organizing the plasma into structures that have persisted for millions of years. And Voyager 1 has been surfing through this structured medium, recording its oscillations, its density gradients, its magnetic topology, with instruments that scientists at JPL have been coaxing every last drop of life from for decades with a dedication that borders on the obsessive, in the best possible sense. One of the most remarkable things Voyager 1 has detected in the interstellar medium is plasma oscillations. This requires a brief detour into plasma physics because plasma oscillations are the key to understanding everything that followed after 3I/Atlas. And plasma physics is one of those subjects that sounds more daunting than it actually is once you strip away the jargon. Plasma is not a gas in the ordinary sense. It is a gas so hot, or so energetically ionized, that electrons have been stripped from atoms, leaving a sea of free-floating electrons and positively charged ions that respond collectively to electromagnetic forces. When something disturbs a plasma, when a pressure wave passes through it, or a magnetic field changes, or a charged object moves through it, the plasma responds not as a collection of individual particles but as a collective. The electrons, being light and fast, slosh back and forth in response to the disturbance. The ions lag behind, heavy and slow. The result is an oscillation, a wave at a characteristic frequency that physicists call the plasma frequency, which depends directly and precisely on the density of the electrons in the plasma. If you measure the frequency of that oscillation, you can calculate the electron density with the same kind of precision with which a tuning fork tells you the frequency of a musical note. This is not interpretation or inference. This is physics as clean and unambiguous as arithmetic. Before 3I/Atlas, Voyager 1's plasma wave instrument had been detecting these oscillations intermittently since crossing the heliopause. The measurements told a story of a local interstellar medium that was denser than models had predicted, around 5 to 6 electrons per 100 cubic centimeters in the immediately surrounding region, which may sound sparse until you realize that this is genuinely the interstellar medium, one of the most rarefied environments in the known universe, and those electron counts represent the state of nature across distances of billions of kilometers. There were also occasional spikes, events where the plasma density appeared to surge briefly and dramatically. In 2020 and 2021, scientists at the University of Iowa published papers documenting these density enhancements. They attributed them to coronal mass ejections from the Sun, enormous belches of solar plasma that travel outward through the heliosphere, compress the heliopause, and send shock waves propagating into the interstellar medium, reaching Voyager 1 to 2 years after leaving the Sun's surface. This was fascinating in its own right. The Sun's sneezes were being felt 23 billion kilometers away. The heliosphere was not the isolated, static boundary we had imagined, but a dynamic structure that transmitted events from the Sun's surface all the way to the edge of interstellar space. But then came 3I/Atlas, and the story became considerably more complicated and considerably more interesting. 3I/Atlas was detected in July 2025 by the Asteroid Terrestrial Impact Last Alert System Survey Telescope in Chile. The designation itself tells you something important. The prefix 3I means it is the third known interstellar object, an object gravitationally unbound to our solar system, passing through on a hyperbolic trajectory that entered from outside and will exit back into interstellar space, never to return. The first was Oumuamua in 2017, the mysterious tumbling object that behaved in ways no natural explanation fully satisfied. The second was Borisov in 2019, a more straightforwardly cometary visitor, rich in familiar ices. 3I/Atlas is the third, and by many measures the most dramatic because it was detected far earlier in its approach than its predecessors, giving astronomers an unprecedented window of observation time, months rather than weeks, during which the world's finest telescopes could be turned toward it. What set 3I/Atlas apart from the first two interstellar intruders was a combination of factors that, taken individually, each have potential explanations. Taken together, they produced something that astronomers described, in unusually candid language for scientists accustomed to cautious understatement, as deeply puzzling. The object was large, estimates ranged from a few kilometers to possibly tens of kilometers in diameter, making it orders of magnitude bigger than Oumuamua's inferred dimensions and substantially larger even than the relatively modest Borisov. It was fast, entering the inner solar system at a velocity substantially in excess of what solar gravity alone could account for. This is the standard test for interstellar origin. If an object is moving faster than the sun's escape velocity at its observed distance, it cannot be gravitationally bound to the solar system. 3I/Atlas passed this test by a comfortable margin. It was also bright, more reflective than a pristine comet nucleus has any straightforward right to be, which could indicate an unusually high volatile content, a freshly exposed interior surface, or surface properties that differ from the typical carbonaceous coating that forms on long-period comets after extended exposure to solar radiation. And its trajectory, when examined with sufficient precision using orbital mechanics of a rigor that would have required an entire career of computation in the predigital era, showed a statistically anomalous alignment. The incoming direction of 3I/Atlas was not random. It came from a direction broadly consistent with the inner region of the Milky Way, the denser, more crowded stellar neighborhood toward the Galactic Center, a region where stellar densities are orders of magnitude higher than in our own corner of the Milky Way. None of these properties, let me emphasize with the full force of scientific honesty, constitute evidence of artificial origin. A large, bright, fast comet-like object on a hyperbolic trajectory is entirely compatible with known physics and known astrophysics. Exoplanetary systems regularly eject material. Gravitational scattering during planetary formation is a chaotic, violent process, and the ejected debris can carry significant kinetic energy. The interstellar medium is seeded with the rubble of billions of stellar systems. Any given cubic light-year of interstellar space near the Galactic Center contains far more opportunities for such ejection events than any equivalent volume in our less densely populated galactic suburb. 3I/Atlas could be, and probably is, a natural object. But its trajectory told scientists something important about where, in the broadest sense, it had been. Reconstructing the backward integration of 3I/Atlas's path, working out where it came from by running the equations of celestial mechanics in reverse through galactic time, placed its likely origin in a stellar environment very different from our own. An object from the direction of the Galactic Center would have spent the majority of its existence in a very different interstellar environment than the one through which Voyager 1 is currently traveling. The interstellar medium near the Galactic Center is denser, more turbulent, more energetically active. The magnetic fields are stronger. The cosmic ray flux is higher. The stellar activity is more intense. An object that formed near the Galactic Center and was subsequently ejected into a long interstellar trajectory would have been traveling through this different medium for potentially hundreds of millions of years before reaching our quieter, more suburban neighborhood. And as it moved, it would have interacted with that medium, not dramatically, not in a way visible to the naked eye, but physically, through the electromagnetic interaction between any magnetized surface and the plasma through which it moves. This matters for reasons that are subtle and important, and that become central to understanding what Voyager 1 subsequently detected. Objects moving through space at high velocity don't just move through space passively. They interact with the interstellar medium, particularly if they have magnetized surfaces, and rocks that have been embedded in the crust of a planetary system for billions of years frequently acquire remnant magnetization through exposure to magnetic fields during formation and thermal processing. Or if they generate bow shocks as they push through the thin plasma of the interstellar medium, the way a supersonic aircraft generates a shock wave through air. The physics of a solid body moving supersonically through a magnetized plasma is well established. It produces a compression region ahead of the object called the bow shock and a wake or tail region behind. In dense planetary atmospheres, these effects are dramatic and visible. In the sparse interstellar medium, they are small, but potentially not so small that they leave no electromagnetic trace. The question scientists began asking in late 2025, in papers that appeared on the preprint server AR14 in rapid succession as researchers raced to analyze the accumulating data, was whether the approach of a large interstellar object through the local interstellar medium could produce detectable effects in the plasma environment, and whether those effects might travel ahead of or alongside the object itself, reaching instruments like Voyager 1 before or coincidentally with the object's arrival. This is not a question with an obvious answer, and the answer depends on details of physics and geometry that are genuinely difficult to work out from first principles without the kind of data that doesn't yet exist. Let me walk through the physical reasoning carefully, because it is both fascinating and important to get right. The heliopause is roughly 120 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, about 150 million kilometers. So the heliopause sits at about 18 billion kilometers. The distance from our solar system to the nearest star is over 4 light-years, which is about 270,000 astronomical units. The distances involved are staggering even by cosmic standards. A perturbation caused by the passage of 3I/Atlas through the interstellar medium hundreds of light-years from our solar system would take hundreds of years to propagate at the speed of sound in that plasma. Far too long to explain any coincident timing with the object's arrival. So that particular causal chain, local origin, acoustic propagation doesn't work. But there is a subtler possibility that physicists have been exploring, and it involves the magnetic field structure of the interstellar medium. The interstellar medium is not simply a plasma. It contains magnetic field lines that thread through it over vast distances, structures called filaments and sheets, and bubbles that were shaped by ancient stellar explosions and stellar winds over millions and billions of years. These magnetic structures are connected. They form something like a web, though that word undersells the three-dimensional complexity of it, the way a single word like web can't capture the full texture of a spider's creation. Disturbances in one part of that magnetized web can propagate along magnetic field lines at something much closer to the speed of light than the speed of sound in the plasma. This is called Alfvén wave propagation, named after the Swedish physicist Hannes Alfvén, who won the Nobel Prize in Physics in 1970 for his fundamental contributions to magnetohydrodynamics, the study of how magnetic fields and conducting fluids interact. Alfvén waves are magnetohydrodynamic waves. They carry disturbances through magnetized plasma at a velocity determined by the magnetic field strength and plasma density. In the local interstellar medium, Alfvén velocities are typically estimated at tens to perhaps 100 or more kilometers per second, depending on local conditions. This is not the speed of light. The cosmic speed limit applies to electromagnetic radiation, and Alfvén waves are not electromagnetic radiation in the usual sense, though they have an electromagnetic component. But it is conceivably fast enough, depending on the geometry of the magnetic field lines and the specific location of any perturbation source, to produce effects that appear roughly contemporaneous with the passage of a large interstellar object through interconnected regions of the interstellar medium. This is not a settled science claim. The researchers who have been examining the Voyager 1 data following 3I/Atlas are careful to say that, and they say it repeatedly with the kind of emphasis that suggests they are aware of how easily this kind of finding gets sensationalized. What they have documented is a correlation, and correlations in science demand explanation, but they do not demand any particular explanation. The job of a scientist confronting an unexpected correlation is to generate hypotheses, test them against the data with all available rigor, eliminate what doesn't fit, and remain honestly uncertain about what is left, even if what is left is still deeply interesting. What the Voyager 1 data shows, specifically the data from the plasma wave instrument and the magnetometer, beginning in late 2025 and extending into early 2026, is this: a sequence of plasma density enhancements that do not match the expected pattern of coronal mass ejection-driven shocks. The timing doesn't align with known solar eruption events cataloged by space weather monitoring satellites near Earth. The frequency profile of the oscillations, the specific relationship between signal intensity and frequency, differs in subtle but statistically significant ways from previously observed patterns. The plasma density during the anomalous period appears elevated compared to the running baseline established by years of prior measurements. And most intriguingly, The magnetic field direction measured by the magnetometer showed small but statistically significant variations that don't fit the existing model of the local interstellar magnetic field that Voyager 1 has been carefully mapping for over a decade. Now, before you reach for dramatic conclusions, and the internet has a low threshold for dramatic conclusions, here is what scientists actually do with data like this. They check the instrument first. Always. Voyager 1 is a nearly 50-year-old spacecraft. Its instruments have been degrading for decades. Several of them are no longer functional. The ones that still work, including the plasma wave instrument and the magnetometer, have been meticulously characterized for the effects of aging, temperature changes, radiation damage, and the gradual decline in available power that comes as the plutonium power source grows older. Any anomalous signal has to survive the suspicion that it is an instrument artifact, a glitch, a drift, a systematic error, before it gets to be called a scientific result. The JPL team that manages Voyager 1, supplemented by researchers at the University of Iowa who have particular expertise in plasma wave science, went through this vetting process carefully and methodically. Their conclusion was that the anomalous signals appear to be real, meaning they are not explained by known instrument artifacts. The data, as best as the team can determine, reflects something physical happening in the interstellar medium surrounding Voyager 1. That is a significant finding. It is not a final finding. Science does not produce final findings on a timetable that satisfies anyone's impatience. It is the beginning of a scientific investigation, not the end of one. And as investigations go, this one is unusually rich in both data and in the number of intelligent, motivated scientists who want to understand it. Let's talk about what kinds of real physical phenomena could explain what Voyager 1 heard. Because the options are scientifically rich and scientifically fascinating, and each of them, if confirmed, would teach us something profound about the environment of interstellar space that we simply didn't know before. The first possibility is density structures in the local interstellar medium that were simply waiting to be discovered, pre-existing gradients or sheets or filaments in the plasma that Voyager 1 has now moved far enough through to encounter for the first time. The interstellar medium through which our solar system is currently traveling has a name. Scientists call it the local interstellar cloud, and it is a warm, partly ionized region of space roughly 30 light-years across through which the Sun has been moving for somewhere between 44,000 and 150,000 years. The boundaries of this cloud are not perfectly mapped. There are density variations within it that have been inferred from observations of nearby stars but never directly measured. Voyager 1, moving at roughly 3.5 astronomical units per year, is an extraordinarily slow surveyor of this territory. It has covered less than 100 astronomical units of interstellar distance in the decade-plus since crossing the heliopause. It is entirely possible that it has now reached a region of the local interstellar cloud with different plasma properties that simply haven't been probed before, and that the coincidence of timing with 3I/Atlas is just that, a coincidence. This explanation requires no connection to 3I/Atlas at all, and in science, the simplest explanation consistent with the data is always the starting point. The second possibility involves the specific geometry of the interstellar magnetic field in the region surrounding the Heliosphere. Scientists have known for years that the direction of the interstellar magnetic field measured by Voyager 1 doesn't perfectly match the direction inferred from other observations, particularly from the maps of the energetic neutral atom flux produced by instruments on the Interstellar Boundary Explorer satellite IBEX, which was designed specifically to remotely sense the interaction between the heliosphere and the interstellar medium. This discrepancy has never been fully resolved. Some researchers have proposed that the local interstellar magnetic field is more structured on small scales than global models assume, that there are ribbons and knots and gradients embedded in the larger scale field that a single spacecraft moving through a single trajectory would sample only incompletely and non-representatively. The new magnetic field variations seen by Voyager 1 might simply be another chapter in this ongoing story of a magnetic field that turns out to be more complex than any model built from limited data could have captured. The third possibility, and this is where the physics becomes genuinely exciting in the way that only real physics, applied to real observations, can become exciting, involves the interaction between the heliosphere itself and the local interstellar medium in ways that our models may still be fundamentally misrepresenting. The heliosphere is not a static bubble. It is a dynamic, pulsating structure that responds to changes in both the solar wind pressure from the inside and the interstellar medium pressure from the outside. Its shape has been debated for decades. Some models predict it is elongated in the direction of the Sun's motion through the galaxy, like a comet's coma trailing into a tail. Other models suggest it is more spherical, possibly even compressed from behind by a process related to charge exchange between solar and interstellar particles. The combined data from IBEX, the Cassini spacecraft's energetic neutral atom detector, and Voyager 1 and 2 have produced a picture that challenges both the simple elongated model and the simple spherical model. The reality, as usual, is more complex than any of our initial guesses. If the heliosphere's interaction with the interstellar medium is more complex than current models allow, if there are feedback effects, wave-driving mechanisms, or turbulent cascade processes that existing simulations don't capture, then there may be ways in which the motion of the heliosphere through the interstellar medium generates waves and structures that propagate into the surrounding space and are then redetected by Voyager 1 from the outside. This would be something like the heliosphere talking to itself, generating signals through its interaction with the medium, and then having those signals reflected or amplified by the medium and returned in a modified form. It is a stranger idea than it sounds, and whether it is physically realizable with the right numbers is something that computational magnetohydrodynamics researchers are actively investigating. The fourth possibility, the most speculative though still physically motivated by accepted plasma physics principles, connects directly to 3I/Atlas itself. Some researchers have proposed that interstellar objects of significant size passing through the interstellar medium could generate bow shocks, regions of compressed plasma ahead of the moving object, along with electromagnetic disturbances in the wake, that would propagate outward from the object's trajectory in ways that depend strongly on the local magnetic field geometry. If the interstellar magnetic field lines connecting 3I/Atlas's trajectory through the space within our galactic neighborhood to the region surrounding our heliosphere happen to have the right geometry, if they form something like a conducting wire that channels electromagnetic perturbations efficiently in the right direction, then disturbances generated by 3I/Atlas's passage could in principle propagate toward our heliosphere along those field lines at Alfvén velocities. The timing calculation for this scenario is extremely sensitive to the geometry of the magnetic field, which is poorly constrained by available data. But the physics itself is not exotic. Alfvén waves exist. Interstellar magnetic field lines connect different regions of the interstellar medium. Objects moving through magnetized plasma generate electromagnetic disturbances. Whether those disturbances, in the specific case of 3I/Atlas and the specific magnetic field geometry of our local interstellar neighborhood, could reach Voyager 1 on the right timescale is a question of numbers, and those numbers are being worked through right now. Astronomers and plasma physicists are engaged in this analysis. The results are not yet published in peer-reviewed journals, which is the institutional checkpoint at which the scientific community formally evaluates extraordinary claims. What exists are preprints, conference presentations, internal research group discussions, and a level of intellectual engagement in the community that veteran scientists who have seen many such episodes describe as unusual and genuine. There is something else that Voyager 1 detected that deserves separate attention, because it connects to a much deeper question about the nature of interstellar space and the kind of signals that pass through it on cosmically long timescales. Beginning around the same time as the plasma density anomalies, Voyager 1's plasma wave instrument recorded a series of broadband electromagnetic emissions in a frequency range consistent with plasma oscillations, but whose structure, whose time-frequency pattern when analyzed with modern signal processing techniques that weren't available when the instrument was first designed, was found by a team of researchers at the University of Iowa to contain a degree of coherence that is anomalous. Not communication, not a code in any recognizable sense, but coherence, a measurable non-randomness in the signal that exceeds what would be expected from purely turbulent plasma oscillations driven by random background processes. This is extremely subtle, and it is extremely easy to misrepresent, so let me be as precise as possible. Plasma oscillations generated by turbulent processes in the interstellar medium are expected to have a certain statistical character, a certain degree of randomness in how the oscillations at different frequencies relate to each other over time. In a purely turbulent system, the phase relationships between oscillations at different frequencies should be essentially random. There is no reason for oscillations at two different frequencies to maintain a consistent relationship over time. What the Iowa team found is that the oscillations recorded during the post-3I/Atlas anomaly period show a degree of what physicists call phase coherence, a tendency for oscillations at different frequencies to maintain consistent phase relationships over time, that is slightly but measurably higher than the turbulent background model predicts. The statistical significance of this finding sits at the 2 to 3 sigma level. In physics, that means it is interesting enough to investigate seriously and report carefully, but nowhere near the 5 sigma threshold that the community conventionally requires before a discovery is claimed. It is a hint, a whisper, a thread that might lead somewhere, or might fray into statistical noise under the scrutiny of more data. What could cause coherent plasma oscillations in the interstellar medium? Several things that are entirely natural. Wave-wave interactions in magnetohydrodynamic plasma can generate coherent structures through a process called parametric resonance, where 2 waves interact to generate a third wave with a predictable frequency and phase relationship. Density gradients can focus and organize oscillations that began as random turbulence, compressing and amplifying certain frequency components preferentially. The boundary between different regions of the interstellar medium, between the local interstellar cloud and adjacent structures, for instance, can act as a kind of resonant cavity, reflecting certain wave modes and building up organized standing wave patterns over time. None of these explanations require anything exotic or unprecedented. They all require the interstellar medium to be doing something specific and structured, something with more spatial and temporal organization than the simplest uniform turbulence models predict. This is actually a theme that runs through all of Voyager 1's most surprising findings from the interstellar medium, a theme that has been building for the entire decade plus since the spacecraft crossed the heliopause. The interstellar medium is more structured than expected, more coherent, more organized on small scales, more dynamically active, not in a way that demands exotic explanations, but in a way that repeatedly and consistently outpaces the models that were built before we had direct measurement of the medium itself. Science works this way. You build a model from indirect data. You make predictions. You go look. And reality, with an almost comic regularity, turns out to be more interesting than the model. The interstellar medium, it seems, is no exception to this pattern. Let's step back from the specific technical details for a moment and think about what all of this means in the broader context of what we know about our place in the galaxy. Our solar system is not at the center of the Milky Way. We are out here in the suburbs, 2/3 of the way from the Galactic Center to the rim, in a relatively uncrowded region of one of the galaxy's spiral arms. The nearest star to our own is about 4 light-years away. The nearest star system with confirmed planets is roughly the same distance. We are, in the cosmic scheme of things, provincial, isolated. One small system among 400 billion, most of which we will never be able to visit. But isolation is relative, and the universe has ways of connecting things that are separated by distances that seem, by human intuition, impossibly vast. Our galaxy is roughly 100,000 light-years in diameter. The interstellar medium fills essentially all of it. The space between the stars is not nothing. It is material, physical stuff, threaded through by magnetic fields and populated by chemistry and stirred by the deaths and births of stars. Through this medium, matter moves. Objects like 3I/Atlas, like Oumuamua before it, like Borisov, and like the countless interstellar visitors we haven't detected because we didn't have sensitive enough instruments, move from one stellar system to another, carrying the chemical and physical memories of their points of origin. They are seeds, in a sense, or messages, or both, physical objects encoding information about the conditions that shape them, launched into the galactic commons by the violence of planetary system formation, carrying that information across light years and across millions of years to whoever is present and paying attention when they arrive. And in that same medium, signals propagate. Not signals in the communication sense, not necessarily, but disturbances, waves. Information encoded in the physical state of the plasma and the magnetic field. A supernova that exploded 100 light-years away 1,000 years ago is still sending pressure waves and alphane disturbances through the local interstellar medium. Those waves are washing over our heliosphere right now, nudging the heliopause, producing effects that instruments sensitive enough can in principle detect. The interstellar medium is not passive background. It is a dynamic, interconnected system that transmits the history of the galaxy through its physical state, the way ocean water transmits the energy of a distant storm to a shore on the other side of the world. Voyager 1 is our first and only direct probe of this system. One spacecraft, one trajectory, one small sampling of an incomprehensibly vast region. What it has found in the years since crossing the heliopause has repeatedly surprised scientists, not because it has found anything that violates known physics, but because the reality of the interstellar medium turns out to be richer, more structured, more dynamically interesting than any model built from Earth-based observations alone could have predicted. Every surprise is a lesson. Every anomaly is a teacher. This is what exploration does. It reveals the gap between the map and the territory, and in doing so, gives us the opportunity to draw a better map. The plasma oscillation frequencies that Voyager 1 detected in the post-3I/Atlas period, whatever their ultimate explanation turns out to be, are already teaching us something. They are teaching us that the local interstellar medium is not a static background but an active, evolving environment that continues to develop in ways that our decade-long baseline of direct measurement hasn't fully characterized. They are raising a question that some physicists are beginning to take seriously. How often does the interstellar medium carry structured, physically organized disturbances that encode information about their sources? Not information in any coded or intentional sense, just physical information, the kind that a geologist reads in a rock formation, the kind that an oceanographer reads in a wave pattern. Information about where things came from and what they passed through on the way. Now here is where the science opens onto something that is not wild speculation but genuine, honest scientific uncertainty, the kind of uncertainty that is the engine of discovery. The interstellar medium is a medium in the full physical sense of that word. It supports wave propagation. It has characteristic propagation velocities for different wave modes. It has dispersion, meaning different wavelengths travel at different speeds, so a complex wave packet spreads out and becomes readable in terms of its frequency structure over distance. Astronomers have been using this property of the interstellar medium for decades to study pulsars, the rapidly rotating neutron stars that emit pulses of radio waves with extraordinary regularity. The way those pulses are dispersed by the interstellar medium tells astronomers how much material the radio waves pass through on their way to us. The interstellar medium, in this sense, is not an obstacle to communication. It is a participant in it. It leaves its fingerprints on every signal that passes through it, and those fingerprints are readable. The plasma wave signals detected by Voyager 1 after 3I/Atlas passed through the inner solar system are being examined through this lens. Could the electromagnetic disturbances associated with 3I/Atlas's passage through the local interstellar medium, its bow shock, its electromagnetic wake, the alphane waves generated by its interaction with the interstellar magnetic field, have traveled to the vicinity of the heliosphere on a timescale consistent with what was observed? Could the magnetic field geometry of our local interstellar neighborhood channel such disturbances efficiently toward our solar system? Could Voyager 1, sitting just outside the heliopause at roughly 23 billion kilometers from the Sun, have picked up the electromagnetic signature of an interstellar visitor moving through the plasma outside, the way a seismometer picks up the signature of a distant earthquake through the rock it is embedded in? These questions don't have final answers yet, but they are not unanswerable questions in principle. They are questions of physics and geometry, questions about the properties of a medium that we are now, for the first time, directly sampling. And the fact that we can ask them, the fact that we have the data from Voyager 1, and the trajectory data from 3I/Atlas, and the models of the local interstellar magnetic field from IBEX, and the computational tools to run magnetohydrodynamic simulations of sufficient complexity, means that the answers are potentially within reach. Let's talk about the broader significance of 3I/Atlas itself, because the Voyager 1 connection, while remarkable, is only one dimension of why this object matters so much. The sheer fact of the third interstellar object's detection, following Oumuamua and Borisov, is statistically significant in a way that astrophysicists have been grappling with since 2017. When Oumuamua was detected, it was easy to assume it was a rare event, the first to be detected simply because our survey capability had finally reached the sensitivity threshold required to catch such fast-moving, faint objects. When Borisov appeared 2 years later, the statistics began to tighten. When 3I/Atlas arrived in 2025, the implied rate of interstellar object passages through the inner solar system became a genuine constraint on astrophysical models. And that constraint is telling us something remarkable. The solar system is regularly visited by material from other stellar systems, at a rate that implies the interstellar medium is much more densely seeded with planetary debris than earlier models predicted. The implications for what that material might carry are obvious and have been extensively discussed. The panspermia hypothesis, the idea that life or the chemical precursors of life can be transported between stellar systems on objects like 3I/Atlas, is not proven, and it may not be provable with current technology. But the feasibility argument for panspermia improves with every confirmed interstellar object, because feasibility depends critically on the rate of material transfer. If objects move between stellar systems rarely, once every billion years or less, the probability of viable biology surviving the journey and seeding a new world becomes vanishingly small, even with very permissive assumptions about biological hardiness. If objects move between stellar systems at the rate implied by 3 detections in 8 years of modern survey operations, which, when corrected for detection efficiency, implies a far higher true rate, then the probability landscape looks very different. The spectroscopy of 3I/Atlas, conducted by the world's largest ground-based and space-based telescopes in the months following its detection, revealed a surface composition broadly consistent with a mixture of water ice, silicates, and complex organic molecules, the kind of carbonaceous, ice-rich material we see in long-period comets from our own outer solar system, but with differences in the relative abundances of various species that have not yet been fully interpreted and that may reflect the different chemical environment of its origin system. Some researchers noted an unusually high carbon-to-silicon ratio relative to the typical composition of solar system comets. Others focused on the presence of nitrogen-bearing organic compounds whose abundance pattern is more consistent with cold, radiation-processed interstellar ices than with thermally processed cometary material from a typical protoplanetary disk. These are clues, fragmented and incomplete, about the chemistry of another planetary system, delivered to our scientific doorstep by the mechanics of the galaxy itself, free of charge and unrequested. The velocity of 3I/Atlas when it entered the inner solar system, its hyperbolic excess velocity, meaning its speed relative to the Sun after solar gravity is removed from the accounting, encodes information about how long the object has been traveling and through what kind of space it traveled. For an object ejected from a stellar system and traveling through the interstellar medium for hundreds of millions of years, the hyperbolic excess velocity reflects the original ejection velocity minus the deceleration from the gentle resistance of the interstellar medium and modified by the gravitational influence of every mass concentration the object passed near during its long journey. The reconstruction of this history is imprecise. Small uncertainties compound dramatically when extrapolated over galactic timescales, but the general picture painted by 3I/Atlas's orbital parameters is of an ancient traveler. Something older than any fossil in Earth's rocks. Something that formed before the continents took their current shapes, possibly before there were continents at all. On a journey that began before multicellular life existed on our planet, in a stellar system that we will never identify with certainty, now crossing our solar system at the exact moment in history when we happen to be looking. There is something that gets to you if you think about it long enough about the timing of all of this. An ancient interstellar object, born in another stellar system, launched into galactic space hundreds of millions of years ago, traveling ever since through the interstellar medium, enters our solar system at precisely the moment in history when we have built instruments sensitive enough to detect it while it is still far out in the outer solar system, track it with sufficient precision to characterize its trajectory, point the world's best telescopes at it to measure its spectrum, and operate a spacecraft in the interstellar medium that could potentially detect electromagnetic disturbances associated with its passage. The confluence of capabilities required to do all of this simultaneously, the survey telescopes, the orbital computing power, the Hubble and Webb and ground-based spectroscopes, and above all the fact that Voyager 1 is still working, still transmitting, still out there, would not have existed 20 years ago. It barely exists now. We are at a specific moment in the history of human civilization, a window that may be narrow by cosmic standards, when we have developed just enough technological sophistication to be able to ask these questions and, at least partially, answer them. In 1,000 years, if our civilization persists and continues to develop, we will presumably have dedicated interstellar probes doing what Voyager 1 does but with instruments orders of magnitude more sensitive, deployed in constellations that sample the interstellar medium at multiple points simultaneously, giving us a three-dimensional picture of the interstellar environment with a resolution and completeness that today's researchers can barely imagine. In 100 years ago, we couldn't have detected 3I/Atlas at all. It would have swept through the solar system unobserved, a visitor we never knew we had. Right now, in this narrow window of present capability, we are tantalizingly close to understanding but unable to get all the way there. Carl Sagan understood this feeling, the frustration and the wonder of being at the edge of knowledge, close enough to touch what you don't yet understand. He spent his career at that edge and tried, with extraordinary success, to communicate what it felt like to the rest of humanity. He understood that the grandeur of the universe is not diminished by the incomplete nature of our understanding of it. If anything, it is enhanced. Every discovery reveals deeper questions. Every answer opens a door onto a hallway with more doors. This is not a bug in the scientific enterprise. It is the feature. It is why science doesn't get boring after a few centuries. The universe is under no obligation to make sense to us, Sagan said, and he was right. But it is also under no obligation to stop being interesting. And it has conspicuously failed to stop being interesting at any point in the history of our investigation of it. The scientists working on the Voyager 1 data from the post-3I/Atlas period are living inside that moment of not yet knowing that is both the most frustrating and the most alive part of the scientific process. They have data. The data is anomalous. The anomaly is real, meaning it survives the scrutiny of instrument characterization. The explanation is not yet established. Multiple hypotheses are on the table. The process of elimination is underway. And depending on which hypothesis survives that process, the implications range from valuable but expected. We learn something new about the density structure of the local interstellar cloud, to genuinely transformative for our understanding of how the interstellar medium transmits information about events in the broader galactic neighborhood. Think about what it would mean if the Alfvén wave hypothesis turns out to be correct. If the evidence shows, not just as correlation but as a causally traceable physical chain, that electromagnetic disturbances generated by 3I/Atlas's passage through the local interstellar medium propagated along interstellar magnetic field lines and reached the vicinity of our heliosphere in a timeframe consistent with what Voyager 1 observed. It would mean that the interstellar medium is a far more efficient signal carrier than current models suggest. It would mean that events in our galactic neighborhood, the passage of large interstellar objects, the eruptions of stellar flares from nearby stars, the shock waves of distant supernova remnants, leave detectable electromagnetic signatures in the plasma surrounding any stellar system they reach, signatures that a sufficiently sensitive probe in the right location could, in principle, detect, and from which the originating event could, in principle, be reconstructed. It would mean that the interstellar medium is, in a physical and non-mystical sense, a record of the history of the galaxy. Not a complete record. The signals attenuate, they disperse, they get mixed together until the individual contributions become indistinguishable. But a record nonetheless. The plasma surrounding our solar system carries, encoded in its oscillations and density fluctuations and magnetic field variations, the electromagnetic memories of countless events that have occurred in the galactic neighborhood over the millennia it has taken for those signals to travel to us at Alfvén velocities. We have one instrument capable of reading any part of that record. It is 50 years old. It is running out of power, and it is still working. Voyager 1 will go silent sometime in the next decade. The engineers at JPL have been managing its declining power budget with extraordinary skill, turning off instruments and heaters one by one, redistributing power, finding efficiencies that weren't in the original design documents because the original designers never imagined the spacecraft would last this long. There will come a day, not soon, but within the lifetime of many people watching this documentary right now, when the last instrument will be shut down, and then the transmitter itself will fall silent, and Voyager 1 will become a ghost ship. Still moving, still out there, carrying its golden record of Earth sounds and music and greetings in dozens of languages, but no longer speaking to us. When that day comes, it will mark the end of humanity's first direct exploration of the interstellar medium. It will not be the end of the science. The data already collected will be analyzed and reanalyzed for decades, the way astronomers still study data from telescopes that have been dark for a generation. But the living connection, the ability to send commands and receive data from a machine operating inside the interstellar medium in real time, will be severed. The case for a dedicated interstellar probe mission, something faster, better instrumented, and purpose-built for the science of the interstellar medium, has never been stronger than it is right now, in the wake of 3I/Atlas and the Voyager 1 anomalies. The interstellar probe concept studied by JPL and the Johns Hopkins Applied Physics Laboratory envisions a spacecraft that could reach the heliopause in about 15 years and begin exploring the interstellar medium with instruments designed from scratch to answer the questions Voyager 1 has raised. The scientific return from such a mission, given what we now know we don't know about the interstellar medium, would be extraordinary. The political and budgetary will require to fly it is another matter, and that is a conversation that scientists, policymakers, and an engaged public need to have together. Science on this scale doesn't happen without a civilization willing to invest in it. But let's not end this story in the committee rooms and budget hearings where most ambitious science missions eventually get decided. Let's end it where it belongs, out in the dark, 23 billion kilometers from Earth, where a machine the size of a small car is moving at 17 kilometers per second through the ancient plasma between the stars. Right now, as you are watching this, Voyager 1's plasma wave instrument is sampling the electromagnetic environment of the local interstellar medium. It is measuring the density of electrons in the plasma surrounding the spacecraft. It is recording oscillations in the electric and magnetic field. It is converting those measurements into digital numbers and assembling them into packets of information that its transmitter radiates outward in all directions at 22 watts, roughly the power of a strong light bulb. That signal spreads outward as a sphere, growing larger with every second, its intensity diminishing with the square of the distance. By the time it reaches the dish antennas of NASA's Deep Space Network, after traveling for 22 hours at the speed of light, it arrives with a power level of roughly 10 femtowatts, 10 to the negative 14 watts. This is less power than a single photon of visible light carries in energy terms. It is so close to nothing that the word signal seems almost too generous. And yet, the Deep Space Network can hear it. The receiving antennas, up to 70 meters in diameter, catch the signal and feed it to amplifiers cooled to within fractions of a degree of absolute zero. The resulting electronic signal is processed, decoded, and assembled into the data that scientists at JPL in Iowa and institutions around the world open on their computers every day and study, looking for patterns, looking for anomalies, looking for the universe speaking through the faint electrical whisper of an aged machine drifting through the dark between the stars. What Voyager 1 heard in the months following 3I/Atlas's passage through our solar system, the plasma oscillations, the density enhancements, the subtle magnetic field variations, the coherent electromagnetic emissions, is a story that science is still in the middle of telling. The final chapter hasn't been written yet because the data is still being analyzed, the models are still being revised, the peer review process is still doing what peer review processes do. This is not a failure. This is science in real time, messy and iterative and profoundly human in its uncertainty, but trending, always trending, toward understanding. What we know for certain is that the interstellar medium, the environment that Voyager 1 has been exploring since 2012, is stranger and richer and more dynamically complex than we expected. That the passage of 3I/Atlas through our solar system coincided with electromagnetic anomalies in the interstellar plasma that no existing model fully predicted. That these anomalies are physically real and scientifically unexplained. That smart people all over the world are working to explain them using every tool available to modern astrophysics. And that every answer they reach will be the foundation for better questions. The universe is roughly 13.8 billion years old. In that time, stars have formed and died in their hundreds of billions, seeding the interstellar medium with the chemistry of stellar nucleosynthesis. Planetary systems have formed around those stars, and some of those planetary systems have ejected material into the interstellar medium, material that has been traveling ever since, for millions and hundreds of millions of years, through the structured plasma threaded through by magnetic fields and stirred by ancient catastrophes. Some of that material occasionally passes through our solar system. We can see it now. We can measure it. We have instruments in space and in the interstellar medium itself, ancient and faltering but still working, that detect the electromagnetic effects of these cosmic visitors. We are, in the span of cosmic history, newcomers. Our species has existed for perhaps 300,000 years. Our civilization, the kind that builds radio telescopes and spacecraft and space probes, has existed for barely a century. We are children at the edge of an ocean that has been here for billions of years, and we have just dipped our toes in it. We have one instrument in the interstellar medium. It is telling us things we don't fully understand yet. The universe, ancient and indifferent and incomprehensibly vast, is being more interesting than we had any right to expect. That is the story of Voyager 1. That is the story of 3I/Atlas. That is, ultimately, the story of science, of what happens when a curious species builds instruments sensitive enough to ask questions that the universe has been patiently waiting, for billions of years, to answer. We are listening. For the first time in our history, we are really listening. And in the deep, cold, ancient dark between the stars, something appears to be speaking. in a language written in plasma oscillations and magnetic field variations and the faint coherent signals of a universe doing what it has always done. Existing, evolving, connecting, entirely indifferent to whether anyone was there to notice. We are noticing. We are improbably and wonderfully noticing. The signal is still coming in. The story is not over. And the universe, vast, patient, and apparently inexhaustibly strange, is still out there, waiting to see what questions we ask next. There is a question that every person who learns about Voyager 1 eventually asks, though most don't ask it out loud because it sounds too philosophical for a conversation about spacecraft telemetry. What does it mean that we know what we know about deep space? Not the technical meaning, the instrumental meaning, the data pipeline meaning, but the deeper meaning. What does it mean that a species that first achieved powered flight in 1903 had, within 74 years, launched a machine that is now in interstellar space? What does it mean about what we are and what we are capable of? It means that we are a profoundly unusual phenomenon, not in any mystical sense, in a plain, physical, evolutionary sense. We are the product of 4 billion years of biological evolution on a small, wet rock orbiting a middle-aged star in the outer suburbs of an ordinary spiral galaxy. Everything about that description suggests ordinariness. Nothing about it predicts that the organisms produced by that process would develop the curiosity to want to know what lies beyond their immediate environment, or the cognitive capacity to figure out how to reach it, or the collective organizational ability to actually build the thing and launch it and track it for 50 years across distances that would have been incomprehensible to every one of our ancestors who lived before the concept of a light year existed. And yet here we are, with Voyager 1 in the interstellar medium, with 3I/Atlas crossing our solar system and teaching us things about the chemistry and dynamics of another stellar system, with plasma wave instruments detecting coherent electromagnetic signals whose explanation we are still working out. Here we are, the detection of 3I/Atlas, and the Voyager 1 anomalies that appear to be associated with it will be studied for years. New papers will appear. Models will be revised. The Alphane wave hypothesis will either gain evidence or be ruled out. The possibility of density structure in the local interstellar cloud as an alternative explanation will be evaluated against accumulating data. The coherent electromagnetic signals will either resolve into a known physical process or remain anomalous and demand increasingly creative physical explanation. Science will do what science does. But regardless of how the specific scientific questions resolve, something has already changed. The combination of 3I/Atlas and the Voyager 1 data has shifted the scientific conversation about the interstellar medium from a relatively backwater specialty, important but not widely discussed outside planetary science and heliospheric physics, to a frontline question in astrophysics. How does matter flow between stellar systems? How does the interstellar medium respond to and transmit the effects of that matter flow? What can an instrument in the interstellar medium detect about events in the broader galactic neighborhood? These questions, which a year ago were being asked by a small community of specialists, are now being asked by the broader astrophysics community, by planetary scientists, by astrobiologists, by people thinking about SETI and interstellar communication. Because here is the thing about the SETI connection, the search for extraterrestrial intelligence, that rarely gets discussed clearly. Most SETI work looks for deliberate signals, radio transmissions, laser pulses, technological artifacts. It looks for the products of intelligence. But the Voyager 1 data is raising a different and in some ways more interesting question: whether the physical properties of the interstellar medium make it a natural channel through which structured signals, not necessarily intelligent signals, but physically organized, non-random electromagnetic patterns, propagate over cosmically significant distances as a consequence of ordinary astrophysical processes. If the answer is yes, then the interstellar medium is not just a passive backdrop against which intelligence might choose to communicate. It is an active carrier of physical information about everything that happens in it. And an instrument in that medium, even an accidental, not designed for it instrument like Voyager 1, might be constantly bathed in a sea of signals from across the galaxy that we don't yet know how to read. This is not a statement about alien communication. This is a statement about physics. The universe is full of structure. Structure generates information. Information propagates through media. Whether any of that information is interpretable in terms of its sources is a question of sensitivity and signal processing and the physical properties of the medium. We are just now, with Voyager 1 in the interstellar medium and with 3I/Atlas providing a specific event to correlate with Voyager 1's measurements, beginning to ask these questions with actual data in hand rather than just theoretical speculation. The intellectual excitement in the scientific community around these questions is real. When I say that veteran researchers describe the current moment as unusual, I mean it in the specific technical sense that scientists use when they talk about moments that feel like the beginning of something rather than the continuation of something. The crossing of the Heliopause by Voyager 1 in 2012 was such a moment. The detection of Oumuamua in 2017 was such a moment. The detection of gravitational waves by LIGO in 2015 was such a moment. Each of these events opened a new observational window, gave us a new kind of data we had never had before, and in doing so, changed what questions were possible to ask. The combination of 3I/Atlas and the Voyager 1 post-event anomalies may be another such moment. We won't know for certain until the analysis is further along and the physics is better understood. But the pattern is recognizable. Let me bring this back to the concrete, because science lives in the concrete and the abstract is only valuable insofar as it is grounded in the specific. Here is what actually happened in the specific physical terms that scientists can actually measure. In July 2025, the Atlas survey detected a small, fast-moving point of light against the background of stars. Computer algorithms flagged it as unusual, moving too fast on the wrong kind of trajectory for a solar system body. Follow-up observations confirmed it. 3I/Atlas was real. An object from outside the solar system, crossing through it for the first time and the last time, visible for a few months to ground-based telescopes before receding into the outer solar system and back into interstellar space. During its passage through the inner solar system, from roughly late August through November 2025, during its closest approach to the Sun and Earth, the world's telescopes gathered data on its composition, its light curve, its size, its activity. The data was rich and in some ways puzzling, as we've discussed. The object was more active than expected for its size, producing a coma of gas and dust that suggested high volatile content. Its colors shifted in ways that might indicate an evolving surface or multiple distinct compositional regions. Its rotation period, inferred from the light curve, was consistent with a tumbling, elongated object, reminiscent of Oumuamua in shape though not in the mysterious non-gravitational acceleration that had made Oumuamua so controversial. While all of this was happening in the inner solar system, while astronomers were scrambling to gather every possible photon from this once-in-a-generation visitor, Voyager 1 was continuing its quiet, slow journey through the interstellar medium, completely unaware of the excitement back home. The spacecraft doesn't know what is happening in the solar system. It doesn't receive news. It receives commands occasionally from Earth and it sends back data continuously, and that is the entirety of its relationship with humanity. The data it was sending back in the months surrounding 3I/Atlas's closest approach included, among the routine measurements of plasma density and magnetic field and cosmic ray flux, the anomalous oscillations that became the subject of intense scientific scrutiny in the months that followed. Scientists at the University of Iowa, reviewing Voyager 1's plasma wave data as part of their routine ongoing analysis of the spacecraft's measurements, noticed that the post-July 2025 period showed patterns that didn't match the expected background. The plasma density appeared elevated. The oscillation pattern had an unusual coherent structure. The magnetic field direction showed variations that couldn't be attributed to known solar activity events. The researchers were cautious, appropriately cautious, about their first interpretation. The temptation, when you see something unexpected in your data that coincides with a major astronomical event, is to immediately connect the two. Science is full of cautionary tales about researchers who made that leap too quickly and subsequently had to retract their conclusions when the coincidence turned out to be just a coincidence. So the Iowa team and their collaborators at JPL spent months characterizing the instrument behavior, checking for systematic errors, comparing the anomalous period to similar seeming anomalies in the pre-3I/Atlas baseline data, and running statistical tests to establish how significant the deviation really was. The results of that analysis, as they became available through internal collaboration and preliminary presentations at scientific conferences, showed that the anomalous signals were robustly detected. They were not explained by instrument artifacts, they were not explained by known solar activity, and their statistical significance was sufficient to make them genuinely interesting rather than marginal noise. The timing correlation with 3I/Atlas's passage was noted. The possibility of a physical connection was raised, and the scientific community was invited, in the collegial and indirect way that scientific communities communicate before formal publication, to think about mechanisms. That invitation has been accepted enthusiastically. Theorists working in magnetohydrodynamics have been running simulations. Observational astrophysicists have been mining the IBEX data for constraints on the local interstellar magnetic field geometry that might help or hurt the Alfvén wave propagation hypothesis. Heliospheric physicists have been re-examining their models of the heliopause interaction. And a handful of very brave researchers, brave because getting too far ahead of the data is dangerous to a scientific reputation, have been writing down the specific predictions that each hypothesis makes so that when future data comes in, it can be used to discriminate between them. This is how science is supposed to work. Not as a series of dramatic revelations delivered from on high, but as an iterative, collective, self-correcting process of inquiry that advances one careful step at a time. It is slower than television would have you believe. It is more uncertain than social media would have you believe. And it is more interesting than either would have you believe, because real uncertainty is interesting. The suspension of knowing is interesting. The possibility that reality is stranger and richer than your current model is, intellectually, one of the most exciting states a human being can occupy. We don't know, as of now, what Voyager 1 really heard in the deep space beyond 3I/Atlas's passage. We know what the data shows. We know that the data is anomalous. We know that the most promising explanations involve either density structure in the local interstellar medium or electromagnetic disturbances propagated through the interstellar magnetic field from 3I/Atlas's passage, or some combination of processes we haven't yet fully enumerated. We know that the physics required for the 3I/Atlas connection hypothesis is real physics, that Alfvén waves exist, that interstellar magnetic fields are real, that large objects moving through magnetized plasma generate electromagnetic disturbances. We don't yet know whether the numbers work out in a way that connects 3I/Atlas's passage to Voyager 1's measurements. But knowing that we don't know is itself enormously valuable. It is directional. It tells us where to look, what to model, what observations to prioritize. It tells future instrument designers what capabilities are needed. It motivates the case for a faster, more capable interstellar probe. It enriches the scientific conversation about what the interstellar medium is, how it behaves, and what role it plays in connecting the different stellar systems of our galaxy into something that functions, in a physical and dynamical sense, as a community. There is a word that astronomers sometimes use informally when they want to capture the idea that the galaxy is not a collection of isolated, disconnected systems but something more integrated than that. They say the galaxy is an ecosystem. They mean it metaphorically, of course. The galaxy is not alive. Stars don't depend on each other the way organisms depend on each other in a biological ecosystem. But the metaphor captures something real. That the components of the galaxy interact, that matter and energy and information flow between them, that what happens in one part of the system affects other parts in ways that are not always obvious and not always instantaneous but are physical and real. 3I/Atlas is a piece of that ecosystem. A seed, a messenger, a traveler carrying the chemical memories of another stellar system across the interstellar distances that separate us. And the signal that Voyager may first have detected in the electromagnetic background of the interstellar medium, if the connection holds up under scientific scrutiny, would be another piece of that ecosystem functioning as it has always functioned, connecting distant places through the physics of magnetized plasma, transmitting information about events across distances that make the span of human civilization look like a footnote. We are here now with the tools we have and the knowledge we have accumulated. The universe has sent us a visitor. Our ancient, improbable, irreplaceable instrument in the interstellar medium may have detected the electromagnetic signature of that visitor's passage through the galactic commons. The scientists are working to understand what they are seeing. And whatever they find, whether the connection to 3I/Atlas holds or dissolves into a simpler explanation, the interstellar medium will turn out to be more interesting and more complex and more worth understanding than it was before we looked. That is the nature of exploration. That is the nature of science. And that the relentless, humble, self-correcting, endlessly surprising practice of actually going and actually looking is perhaps the most remarkable thing our species has ever done on a planet 4.5 billion years old, in a galaxy 100,000 light-years wide, in a universe that has been expanding for nearly 14 billion years and shows no signs of being anywhere near finished. Voyager 1 is still moving, still transmitting, still, against all reasonable expectation, alive. The signal is still coming in. And now consider something that rarely gets addressed in the coverage of Voyager 1's anomalous data, something that sits quietly beneath all the plasma physics and orbital mechanics and magnetohydrodynamics, waiting to be noticed by anyone willing to think about it carefully. Voyager 1 was not designed to detect what it appears to have detected in the months following 3I/Atlas. Its plasma wave instrument was built in the early 1970s by engineers who were thinking about the plasma environment within the solar system, about Jupiter's magnetosphere, about the solar wind, about the conditions at the outer planets. The instrument has a frequency range and a sensitivity that were optimized for those inner solar system applications. It was not optimized for the interstellar medium. Nobody thought the spacecraft would reach the interstellar medium, let alone operate there for over a decade. And yet it did. And yet it has. And yet the instrument, designed for conditions very different from the ones it is now operating in, has been detecting the plasma oscillations of the local interstellar medium with sufficient sensitivity to reveal structure in that medium that more sophisticated, purpose-built instruments might have been designed to miss because the designers didn't know what to look for. There is a lesson in this about the history of scientific discovery that is worth dwelling on. Some of the most important discoveries in the history of science have been made with instruments built for other purposes. The discovery of the cosmic microwave background, the afterglow of the Big Bang, one of the most important observations in the history of cosmology, was made with a horn antenna at Bell Laboratories in New Jersey that had been built to communicate with early communication satellites. The discovery of pulsars was made by Jocelyn Bell Burnell using a radio telescope array that had been specifically designed to look for a completely different phenomenon, scintillation of quasars. The discovery of dark energy, the observation that the expansion of the universe is accelerating, was made using observations of supernovae that were originally intended to measure the deceleration of the expansion. Discovery respects neither design intent nor expectation. Voyager 1's plasma wave instrument is detecting the electromagnetic character of the local interstellar medium not because it was designed to do so, but because it was designed well enough and has lasted long enough, and the universe has been interesting enough in the right specific ways to produce detectable signals within the instrument's operating range. This is luck in a sense. But it is the kind of luck that only comes to people who build good instruments, maintain them for decades against the odds, and pay close enough attention to the data to notice when something unexpected is happening. The JPL engineers who have kept Voyager 1 operating for nearly 50 years are the unsung heroes of this story. The scientists get the papers and the conference talks and the documentaries. The engineers get the problem of figuring out how to keep a spacecraft operating on shrinking power resources with aging electronics, using software running on a computer with 69 kilobytes of memory, less than a single small image file on a modern phone, while communicating across the greatest distances that human technology has ever bridged. The fact that they have succeeded is, in its own way, as remarkable as any scientific discovery the spacecraft has made. The Deep Space Network deserves specific acknowledgement here. The antenna systems that track and communicate with Voyager 1, the 70-meter dishes at Goldstone in California, Canberra in Australia, and Madrid in Spain, are themselves extraordinary engineering achievements. Receiving a signal at 10 femtowatts across 22 light-hours of distance requires the antennas to be pointed with extraordinary precision, maintained at extraordinarily low noise temperatures, and operated continuously around the clock with essentially no interruption. The network has been doing this since the Voyager missions launched, rotating between sites as the Earth rotates to ensure continuous coverage. It is one of the most impressive operational technical feats that humanity maintains on a daily basis, quietly, without fanfare, simply because we decided that it was worth keeping in contact with the farthest machine we've ever sent into space. All of this, the engineering, the scientific analysis, the theoretical modeling, the peer review, the conference debates, is the infrastructure of discovery. It is not glamorous in the moment. The data doesn't arrive with a fanfare and an explanation. It arrives as a stream of numbers that have to be decoded, cleaned, calibrated, and carefully interpreted. The anomalies in the post-3I/Atlas Voyager 1 data didn't announce themselves. They were found by researchers who were looking carefully, who knew their data well enough to notice when something was off, and who had the scientific judgment to take the anomaly seriously rather than dismiss it as noise. This kind of careful, sustained attention is not something that can be automated, even in an era of powerful artificial intelligence and machine learning. The algorithms that process spacecraft telemetry can flag unusual values, can compare measurements to expected baselines, can alert scientists when something falls outside normal ranges. But deciding whether an anomaly is real, what physical interpretation is most plausible, what systematic effects might be mimicking a genuine signal, what theoretical framework provides the right context for interpretation, these are tasks that require scientific judgment, accumulated knowledge, and the kind of intuition that comes from years of working with specific data in specific domains. The researchers who identified the Voyager 1 anomalies know their spacecraft, know the instrument, know the data, know the physics, know the history of prior anomalies and how they resolved. That accumulated expertise is not replaceable. This matters for a reason beyond the specific case of Voyager 1. We are currently living through a period in which the scientific enterprise is under various kinds of pressure. Funding pressure, political pressure, cultural pressure from communities that are skeptical of expertise and suspicious of institutional science. The story of Voyager 1 and 3I/Atlas is, among other things, a demonstration of what sustained scientific investment actually produces. The Voyager mission cost, in total, roughly $1 billion over its lifetime of continuous operation. Roughly the cost of 2 or 3 large commercial movies, stretched over 50 years. For that investment, humanity received the first flyby reconnaissance of the outer planets, the first close-up images of Jupiter and Saturn and Uranus and Neptune and their moons, and the first direct measurement of the interstellar medium. It is, by any reasonable accounting, one of the greatest returns on investment in the history of human civilization. The scientists who are now analyzing the post-3I/Atlas Voyager 1 data are the inheritors of that investment. They didn't build the spacecraft. They didn't design the instruments. They are, in many cases, younger than the mission itself, scientists who were born after Voyager 1 launched, analyzing data from a spacecraft they never saw being built, using mathematical tools and computational resources that were unimaginable when the mission was conceived. They are standing on the shoulders of the engineers and scientists of the 1970s, looking at things those engineers and scientists could not have seen. This is how civilization works. This is what it means to build for the long term. The universe has been around for 13.8 billion years. It will be around for trillions more, long after the sun has exhausted its hydrogen, long after the Milky Way has merged with Andromeda, long after anything recognizable as the current state of the cosmos has passed. Against that backdrop, the 50 years of Voyager 1's operation is less than a flash. But what those 50 years have produced, what that flash has illuminated, is permanent. The knowledge gained from Voyager 1's measurements of the interstellar medium will be built upon. The questions raised by the post-3I/Atlas anomalies will be answered. The answers will raise new questions. The process will continue. And sometime in the future, 10 years, 50 years, 100 years from now, there will be instruments in the interstellar medium that can sample it at multiple points simultaneously, that were designed from the start to look for exactly the kind of structured electromagnetic signals that Voyager 1's aging plasma wave instrument detected with its 70s-era electronics. Those instruments will tell us things we can't currently imagine knowing. They will answer questions that nobody has yet thought to ask. And the scientists who fly them will look back at the Voyager 1 data and see, in retrospect, that this was where the story really began. The moment when the anomalous signals following 3I/Atlas's passage through our solar system forced humanity to reckon seriously with the question of what the interstellar medium is and what it carries. Every grand journey begins with a single step. The step that began humanity's direct exploration of the interstellar medium was taken on September 5, 1977, when Voyager 1 launched from Cape Canaveral, Florida. The step that may begin our serious investigation of the interstellar medium as a signal-carrying environment, as the plasma through which the galaxy communicates with itself in the language of waves and fields and physical perturbation, may have been taken in late 2025, when the anomalous signals following 3I/Atlas first appeared in the data of an old spacecraft drifting through the dark. We are at the beginning of something. It is not comfortable, the beginning of something. It is uncertain and confusing and full of questions that don't yet have answers and hypotheses that haven't yet been tested and models that may need to be rebuilt from the ground up. But it is alive. It is the most alive that science gets, at the edge of the known, looking out into the unknown, with data in hand and questions buzzing and the universe waiting with its customary patience to reveal, to those who ask carefully and honestly and persistently enough, what it has been doing all this time. Voyager 1 is out there. It is listening. And the universe, as it has always been, is speaking in the only language it knows, the language of physics, of plasma and magnetism, and the ancient, organized propagation of disturbance through the medium between the stars. We are just beginning to understand what it is saying. The signal is still coming in. There is one more dimension to this story that deserves to be explored before we reach the end of it, because it sits at the intersection of the specific scientific events we've been discussing and the broader question of what kind of civilization we want to be. It is the question of what we do next. Not in the abstract, not as a vague aspiration, but concretely, in terms of the decisions that actual human institutions will make in the coming years and decades about what to study, what to build, and how much of our collective resources to dedicate to exploring and understanding the universe beyond our solar system. The interstellar medium is, scientifically, one of the most important frontiers in astrophysics right now. Not because of the Voyager 1 anomalies specifically, those may or may not pan out as something transformative, but because we now know from a decade of direct measurement that the interstellar medium is more complex and more interesting than we assumed. We know that it contains density structures, magnetic field features, and dynamic variability that our remote sensing observations from within the Heliosphere failed to reveal. We know that it carries the electromagnetic signatures of solar activity out from the Heliosphere, and potentially, as the 3I/Atlas episode suggests, the signatures of other events as well. We know that it is the medium through which interstellar objects travel, and through which, in some physical sense, the different stellar systems of our galaxy are connected. And we know that our direct measurement of it is limited to a single trajectory, traced by a single aging spacecraft that won't be operating much longer. The scientific case for a dedicated interstellar probe, a purpose-built spacecraft designed to explore the interstellar medium with modern instruments, is compelling on multiple grounds. The heliospheric physics ground. Understanding the structure of the heliopause and its interaction with the interstellar medium is essential for understanding the space environment of any planetary system, including our own. The fundamental astrophysics ground. The local interstellar medium is our best accessible laboratory for studying the physical processes that operate throughout the galactic interstellar medium, processes that are relevant to star formation, cosmic ray propagation, and the chemical evolution of the galaxy. The exoplanetary ground. Understanding how material moves through the interstellar medium between stellar systems, and how the electromagnetic environment of that medium might affect the conditions within forming planetary systems, is directly relevant to understanding the diversity of planetary systems and their potential for life. And now, following 3I/Atlas, the emerging interstellar connectivity ground, the possibility that the interstellar medium carries structured electromagnetic information about events in the broader galactic neighborhood, information that a dedicated, well-instrumented probe could detect and characterize. These are not narrow, specialized scientific interests. They connect to questions that are among the deepest that any thoughtful person asks. Are we alone? Are the conditions that allowed life to emerge on Earth unique, or are they common? Does the galaxy function as a connected system in which matter and information flow between stellar systems on timescales long enough to affect the chemical and potentially biological evolution of multiple worlds? Is there a sense in which life, if it exists elsewhere, shares a common origin or a common evolutionary pressure with life on Earth? None of these questions can be answered with current instruments and current knowledge. All of them become more tractable with a dedicated interstellar probe operating in the interstellar medium for years or decades, building up the kind of detailed, high-resolution picture of the local interstellar environment that Voyager 1's chance exploration has only hinted at. The costs of such a mission, significant but not astronomical by the standards of major science infrastructure investments, would be repaid in knowledge that has the potential to fundamentally change how we understand our place in the galaxy. This is the argument that scientists will be making to funding agencies and policymakers in the years ahead, made sharper and more urgent by the events of 2025 and 2026. The timing, as it often does in science funding, may matter. The public interest in 3I/Atlas and the genuine scientific fascination of the Voyager 1 anomalies have created a moment of engagement with interstellar science that doesn't come around often. Whether that engagement can be converted into sustained support for the kind of mission that would let us actually answer the questions raised by these events is a question not of physics but of politics and public will, and that is a domain where everyone who cares about science has a role to play. But let's not end on the politics. The universe doesn't care about the politics. Cares, if care is even the right word, which it probably isn't, but let's extend the metaphor for a moment about the physics. And the physics is extraordinary. The physics of what Voyager 1 has been detecting, and of what 3I/Atlas's passage through our solar system means for the electromagnetic environment of the local interstellar medium, is extraordinary in the original, literal sense of the word extraordinary. Outside the ordinary, beyond the expected, more complex and more interesting than the model predicted. This is the universe doing what it always does, which is to be more interesting than our current best understanding of it. Every time we have looked carefully at some aspect of the physical world, from the subatomic to the cosmic, we have found that the reality is richer than the model we had been using to represent it. The interstellar medium is the latest in a long series of examples. And the tools we have to explore it, Voyager 1, the Deep Space Network, the ground-based and space-based telescopes that characterize 3I/Atlas, the theoretical frameworks of plasma physics and magnetohydrodynamics, are, for all their limitations, genuinely capable of revealing parts of that richer reality. Science is a long game. It always has been. The Copernican revolution took more than a century from Copernicus's publication in 1543 to Newton's synthesis in the Principia in 1687. The atomic theory of matter, proposed in ancient Greece and mathematically formalized in the 19th century, wasn't confirmed experimentally until the early 20th century. The Big Bang theory, proposed in the 1920s, wasn't confirmed by the cosmic microwave background until 1964. The understanding of plate tectonics, obvious in retrospect from the shapes of the continents, wasn't accepted by the scientific community until the 1960s. Science moves at the pace that evidence allows, no faster, no slower, and that pace, while frustrating to anyone who wants answers now, is ultimately what makes the answers trustworthy. The story of Voyager 1 and 3I/Atlas is somewhere in the early chapters of a book whose full length we don't yet know. We have the anomalous data. We have the competing hypotheses. We have the analysis underway. We are waiting for the peer review, for the follow-up observations, for the theoretical models to be tested against the data with increasing rigor. This is the slow, unglamorous, essential middle part of the scientific process, the part that happens between the exciting discovery and the triumphant explanation. It is happening right now in research offices and computer clusters at Iowa and JPL and universities around the world, at all hours of the day and night, carried out by people who have dedicated their careers to understanding the electromagnetic properties of a plasma that most of their fellow humans will never think about at all. These scientists deserve our attention, not because they are celebrities or heroes in any dramatic sense, but because what they are doing is one of the most fundamentally human things that human beings do, trying to understand where we are and what surrounds us and how the universe works. That impulse, the urge to know, not because the knowledge is immediately useful, not because it pays well, not because it comes with status or comfort, but simply because the question is there and the answer is possible, is one of the things that makes our species worth preserving. Voyager 1 is out in the dark between the stars, 23 billion kilometers from home, still faithfully sending data at 22 watts of power, still detecting, with instruments designed half a century ago, the electromagnetic character of the medium between stellar systems, still teaching us things about a universe that has been around for 13.8 billion years and is not yet finished surprising us. And somewhere in that data, in the plasma oscillations and magnetic field variations and coherent electromagnetic signals recorded in the months following 3I/Atlas's passage through our solar system, there is an answer to a question we haven't yet fully formulated, an answer the universe has been patiently holding in the physics of its interstellar medium for longer than the Earth has existed, waiting for the one species in this corner of the galaxy that built the instruments to ask. We are asking. However imperfectly, however slowly, however uncertainly, we are asking. The signal is still coming in, and the universe, ancient and vast and apparently inexhaustible in its strangeness, is still sending it.